All right, hello, good morning everyone. My name is Atilla Turedi. I work as a technical specialist for the electrical architecture at JLR, and today we'll be talking to you about a collaborative prove-out project that was done between Analog Devices and JLR, which was looking at low latency applications in a software centralized Ethernet-based architecture, which moves us towards the SDV. So I'll kick us off with a brief summary of the JLR's definition of software-defined vehicle and how that differs from the traditional domain-based architecture. So if you haven't heard about the word SDV already enough, this will be your opportunity to catch up, hopefully. We'll talk about the remote control protocol and the role of software in the central compute, and then explain why suspension is a suitable candidate for being controlled remotely, but also why it is a system that's worth proving out. Later, Eduardo will be showing you the experimental setup and the results that we achieved. We'll touch on a very critical subject, especially for systems like suspension, and that is synchronicity. And lastly, we'll briefly mention what the impacts of having additional nodes on the same network as the suspension is as an interference source. So, software-defined vehicle and the role of hardware. So I think an architecture can only be software-defined if the underlying platform and the hardware enables it. While technically, for a domain-based architecture, it's not absolutely impossible for it to get itself aligned to a software-defined approach, it is so limiting that it becomes impractical. So the architecture needs to shift towards something that's more accommodating of the fundamental principles of software-defined vehicle. So let's start with domain-based architecture and its key advantage, in my opinion, and that is the organization. So in the traditional split of responsibilities between OEMs and suppliers, OEMs are responsible for generating the system level requirements and having the right set of standards that then you pass on to a supplier, and the supplier is responsible for delivering the hardware and software that meets those requirements in a neatly contained black box kind of an approach. So your main responsibility or priority as an OEM is to make sure you have the right set of requirements that delivers the domain functionality, and your main asset as an OEM is that domain level expertise. Now, this is organizationally advantageous because you have these groups of closely coupled people in domains with domain expertise. They work together to deliver that domain, and they only interact with other domains or rest of the business over some very clearly defined interfaces. And that is both at an organizational level, but that also reflects how you design the architecture of the car as well. And that also becomes a disadvantage when you think of the architecture, because those interfaces stay at an abstracted level, and the raw data, the real data, is always hidden behind the domain boundaries. So this is a very important key disadvantage of domain-based architecture. Now with domain-based architectures, due to what I just explained, and also the fact that multiple peoples and suppliers need to come together to deliver those customer-facing features eventually, it's also very difficult and a long process to introduce new features or improve the existing ones. It takes many months and lots of people involved. Due to the way that software is established in domain architecture, not to say that domain-based architecture is not secure, but because of the way you establish it, it's also very unwelcoming to change as well. And lastly, in a domain-based architecture, the off-board side is always seen as just another domain, and it's not a natural extension of the vehicle's architecture. So now that we talked about the main advantage of domain architecture, but also its pain points, it will be simpler to see where zonal and SDV approach comes in to fix some of those challenges, but why also it's a challenge for OEMs to make that transition. So in the SDV, OEM has to own the platform, and in that platform, different domains will be living side by side. This is an organizational challenge because you as a business need to come together from different domains, different people, and you need to define a platform that works for everyone's needs and is also efficient and is also scalable and is flexible. So that's an organizational challenge. But once you establish the fundamentals of SDV and zonal architecture, you'll surely start getting the data freedom. So the data will not be hidden behind those boundaries anymore. You'll have much more simpler time deploying new features and improvements to the existing features. And because SDV and zonal architecture is fundamentally reliant on having an Ethernet-based backbone, and which has well-known security solutions, that side will be simpler as well. And lastly, in an SDV architecture, the off-board side will become a much more coherent part of the vehicle's architecture, and it will just become a natural extension. Now, breaking a domain apart in a zonal architecture has its, of course, technical challenges. So you have some very tight control loops associated with your domain's end-to-end latencies, etc. And any delays that you introduce into that system will come back as noticeable phase lags to actual customer-facing features, and that is not acceptable. So when we are making this transition from the domain-based architecture to SDV, our at least minimum expectation is to be able to meet today's domain-based performance in terms of latency, synchronicity, etc. But that's not enough, because SDV needs to come with some added value. And that added value should allow us easier time improving features, enhancing algorithms, getting more data out of the car. So SDV should give us more headroom compared to today's domain architecture. Now, what does a domain look like? You have your domain ECU, you have your actuators and sensors that are distributed across the car, and the entire software, including the software that hosts the domain algorithm and the one that makes it possible to communicate with the rest of the car architecture, is all hosted on that domain ECU. And the data is abstracted, encapsulated in the form of vehicle-level signals, and that is what is shared back and forth between different domains and this particular domain. So this domain never allows its raw data to go out of the domain, nor does it allow its actuators to be controlled from anywhere else in the car. It doesn't allow direct control of its actuators. And this is what it looks like at a physical level. Like I said, you have the sensors and actuators distributed across the vehicle wherever they need to be, because they are delivering a particular functionality there. And then wherever possible, you package your domain ECU geometrically, and you have these long wires coming from sensors and actuators across the car to that single domain ECU. And sometimes a single domain ECU isn't enough. You need to have these multiple helper ECUs, and you might end up with a domain network, and that will have some wires running across the car as well. So you can imagine how this becomes gradually more and more challenging as you start introducing more domains into this picture. Now, in the remote I/O concept, what we have is actuators and sensors exactly in the same places, but now the domain logic has moved to a central compute module somewhere in the car, along with every other domain's logic. And now you have zonal modules in strategic locations in the car, also distributed across the vehicle, connecting to those actuators and sensors. But the zonals, their responsibility is just to be a bridge between the sensors data and controlling of the actuators. And this is how that manifests itself physically. Zonals are in strategic locations. You have much more shorter wires to your sensors and actuators, and there is an Ethernet backbone to the main compute where the logic lives. You can imagine how this is infinitely more efficient from a harnessing and geometry point of view. You have much shorter wires. You don't have wires that are crossing body structures. You don't have those wires carrying raw signals over long distances. You have less splices, less inline connectors, and so on and so on. Now, before I hand it over to Eduardo, just a few words on the suspension use case. So we think centralizing software makes it easier to improve and deliver features. This is absolutely the case for the suspension. It also eliminates hardware from the car and reduces harness that is only there to deliver the suspension capability. And suspension as a system is a good challenge to focus because it has a highly distributed number of sensors and actuators all around the car. You have some very tight control loops associated with the operation of suspension, and you have synchronicity requirements. And in JLR cars, there is a constantly evolving demand for the capabilities of the underlying platform that delivers suspension because the feature itself is constantly evolving. So it would be nice to have that headroom so we can scale the capability without changing the hardware and software. So we think in order to make that possible, we need to minimize the software that is outside the central compute unit. That gives us less software to maintain, less software to update, less software to focus on bug fixing, etc. But it is also a means to have reduced latency because you would have less software contributors to the overall end-to-end latency. So now I will hand it over to Eduardo for him to take you through the experimental results and show you the setup, which has given us confidence towards SDVization of our domains. Thank you. Please, Eduardo.
Thanks, Mete. So, how many of you have implemented the control loop recently? And how many of you have trouble with latencies while implementing it? So, now imagine doing all of that over the network on 10BASE-T1S. I'm Eduardo Santos Navarro, and in this section of the presentation, I'm going to talk about the proof of concept we built with JLR on the suspension control use case. Oops. Okay. So the scope of this proof of concept is to demonstrate that using E2B technology within a 10BASE-T1S network, we are able to meet all suspension control requirements. The E2B technology is the analog device's remote control protocol, which main objective is to remove the software in the edge nodes. And in the end, is the work on the software centralization. The two main objectives of this proof of concept is to deliver an in-depth timing analysis that is going to permit have better timing estimations for this use case and other use cases in 10BASE-T1S. And then, when implementing a control loop over the network, it's very important to know how much time we are going to spend in the data transmission in the network. So we're going to provide that number, and we will know how much time we do have for computation for the suspension control algorithm. This proof of concept consists on a 5-node network. We're going to have a Mag5 node that is going to be connected with the Open Alliance SPI to the central compute unit. And the idea is that the central compute unit will address the ADC sampling request and ADC actuation and SPI actuation request to the rest of the nodes. The rest of the nodes, they are the zonal nodes indicated in there. They are all hardware, are not going to be located in each of the wheels of the car. So they're going to take care of getting the sensor data from the accelerometers and height sensor from the chassis, and then to actuate to the different coils and solenoids of the chassis. That actuation to the different coils and solenoids is through an external driver that is SPI interface. So that's why we're using that SPI. For this proof of concept, we are not using the sensors and actuators that are located in the chassis. We're using a system equivalent. So we have a wave generator that is generating 3 analog signals that are going to be sampled in the ADC integrated in our E2B zonal device. And instead of using the solenoid driver, we're using 2 SPI interface DACs that has 4 channel seats, making a total of 8 SPI transactions to drive or to simulate the driving of all coils inside the car or in each of the wheels. So at the end, we will have the wave generator signal that will be sampled, and it could be ideal, or that's the objective, to regenerate that signal on the output of the DAC channel. So at the end, using an oscilloscope, we will compare and see both of them and see if everything's working well. So the suspension use case has some challenges. The first one is the iteration time. As Mete mentioned, it has a tight iteration time that is 2 milliseconds. So to make a full iteration, we need to make ADC samples in the 4 remote nodes, then send the data back to the central compute unit, run the suspension algorithm or the computation that is in this proof of concept, send the actuation data back to the 4 zonals, and make the SPA transactions. To all that, we have that time of 2 milliseconds. On top of that, we have a requirement for the synchronicity of the ADC sampling. So all data has to be time sync when gathered. And that means we have a time window of 100 microseconds for all ADC samples happening in the 4 remote nodes. At the end, this is going to work like the central compute unit is going to address an ADC sample request, and it will start the sampling in the 4 nodes. We are going to make 3 samples per node, and in this diagram, it looks like the samples are done sequentially. It depends on the synchronization strategy we are having. This can look like something in parallel for best synchronization strategies. Then for the actuation, we have a very similar requirement that is a time window of 100 microseconds for all SPA transactions happening in all nodes. So it's going to work the same. The central compute unit will send the SPA actuation request with the data to recreate the sample data in the DAX, and all nodes will start the SPA actuation. With the proper synchronization strategy, all the actuation may look like parallel, and the key idea of this slide is that we have that window of 100 microseconds for the full SPA transaction happening. So we have a requirement of 2 milliseconds. That requirement came from the all distributed architecture from GLR, and in our implementation of this proof of concept, we've reached a time of, or worst case time of 1.32 milliseconds. So we are meeting the requirements that Mete provided to us, and we are having a remaining time available for computation of 680 microseconds. That time is enough for running the suspension control algorithm, as in a software centralized architecture, the central compute unit will run very fast, maybe at gigahertz, so that's more than enough time for running the suspension algorithm. And how this is looking in the oscilloscope, that was one of the key objectives of this proof of concept. So we can see in there's the green signal, that is the wave generator 1, and the blue signal is the DAC output. And as we can see, it's following perfectly the green signal with an updated step of 2 milliseconds. So this was the desirable behavior of the demo. Then one of the key deliverables for this proof of concept was the in-depth timing analysis. So in here you can see a sequence diagram with all latency contributors and the values of each of them. The first latency contributor is the time that we take for the ADC sampling in the 4 remote nodes. This is making 3 samples in the 4 remote nodes. It's 12 microseconds, which is meeting by far the requirement of 100 microseconds we had. Time is that low because all the ADC sampling is happening almost in parallel. Then when data is ready in the different tonal nodes, it is transmitted via 10^1s and OSPI to the central compute unit. Then in the central compute unit, there's some ADC data processing and generating the actuation frame that is transmitted again via OSPI and 10^1s to the tonal nodes. Then in the tonal nodes, the SPA transaction will start, and it's taking 97 microseconds time, which is meeting the synchronization requirement of 100 microseconds, but it's quite tight. Most of that time is due to the SPA actuation is in series, and it's running at 2.5 meg speed. So that's almost of that time is the time that it takes to make the SPA actuations. There's some room of improvement on all these values in the OSPI transport time, for example, and also in the SPA actuation we could parallelize that. But at the end we are having a round trip time that meets all the requirements from GLR. And how close is this implementation to the real use case that is going to be implemented in the car? So the multi-drop network is not quite accurate to what is going to be in there. What we would expect is having a multi-network architecture. So the zonal nodes that has connected sensor and actuators for the chassis are located in different networks. And those networks will live with different nodes that have sensors and actuators for other use cases. So that has some implications to the system. And the first one is that what happened with the values we got from this proof of concept. So the multi-drop network is a worse case than this multi-network one. As for getting all data from ADC samples, we need to wait for a full PSA cycle. And then to make the actuation of the SPI actuation, we need to send bigger frames to actuate the 4 remote nodes. That's not going to happen when separating everything in different networks. Then another key aspect, when moving to a multi-networks architecture, we will need to have switches in the architecture, in the design. And that will be adding some extra new delay contributor, that is the switching latencies, that will need to be investigated in the future. And this moving to the multi-network architecture reveals also two big challenges. And the first one is making synchronization of nodes in different networks. So when you have all nodes in one network, the network permits it, you could synchronize nodes using multicast frames. That is a very basic way of synchronizing. But when moving forward to a multi-network use case, it's not possible to do that. Then also, when adding or when separating different networks and adding extra nodes, it will be needed to evaluate the impact of extra nodes to the network and have an ensured network design that is going to make the requirements be met by all cases. It doesn't matter what's happening in the network. So first of all, talking about synchronization, we had to implement two synchronization strategies in the demo. The first one is the multicast frame I mentioned before. So it's the basic synchronization strategy, and it's sending a multicast frame with multiple packets on it, and each packet is pointing to one of the nodes in the system. So the time diff between the start from node 0 to node 3 is going to be the time that it takes for each node to decode the big frame and to reaching the data that it's pointing to itself. There's some pros and cons on this synchronization strategy. The pros is that it's very efficient for the data in the frame, as everything is payload. Maybe not payload pointing to each of the nodes, but it's payload that is going to be used in the interfaces. Then the time between the starts or the synchronization that we achieve is 4.8 microseconds time, which is good enough to meet the suspension use case requirements for synchronicity on sampling and actuation. And the bad thing is that we need to use multicast frames that may not be desirable for all networks, and also it cannot be used to synchronize nodes in different networks, which is a big no when moving forward on this use case. These are the results from the logic analyzer when implementing this multicast synchronization strategy. So in there you can see the different chip select signals, and you can see that from chip select 0 to chip select 3 there's a time diff. That's the time it's taking to decode the full frame, and that's adding that 4.8 microseconds time to the total SPI transaction time. So that's making a total of 97.3 microseconds, which meets the requirement from synchronicity, but it's quite tight. Then we have the more sophisticated synchronization strategy that is using GPTP. In this case, it will be needed to have a GPTP grandmaster in the network. It could be located in the central compute unit or in another part of the network. It doesn't matter. But the good thing is that all nodes in all networks will have the possibility to be synced to that GPTP grandmaster timestamp. And what is best is that all nodes will have the possibility to actuate at a certain timestamp from GPTP timestamp. So that means, for example, we can send a command that says make an ADC sample or at time 44 milliseconds. So when the GPTP grandmaster timestamp reaches that 44 milliseconds, the ADC sample will start automatically. There's some pros and cons of this strategy as well. So the big pros are that it's very well synchronizing. We are getting results on this demo from 0 to 30 nanoseconds, which are much better than the previous synchronization strategy. And it can be implemented to synchronize nodes in different networks. So that's what we would need when moving forward on this use case. Then as a bad thing, it is adding a little more extra network complexity. It is required to have sync and follow-up messages in the network, constantly running to synchronize the different nodes to the GPTP grandmaster timestamp. These are the results for the GPTP timestamping synchronicity. So as we can see in the lyrical nature, we will need to make a zoom to see the time diff between the chip selects going low. And with that synchronization strategy, we're getting a total value of 92.5 microseconds for the full SPI transaction time, which is also meeting the requirements from the suspension use case. And then we have another challenge that was what's happening with other nodes in the network. So when adding other nodes in the network, they're going to take their transmit opportunity time, and they're going to send their maximum data frame when they require, and that will have an impact on the latency of the control loop. So the good thing is that 10^1s, when working in PLC mode, it has a bounded maximum latency, so we can take benefit of that. But there will be needed some network design work to ensure that we are meeting the requirements every time while running the critical control loop. So for that, there's some strategies that can be implemented. For example, this frame size optimization. You can configure the size or the maximum frame size of each of the nodes. So when each node gets payload, the amount of payload enough or the payload that was configured, it will automatically packetize that data and send it when the transmit opportunity permits it. So what this is making is this giving a deterministic or selecting which time is going to take each node in the network when getting its transmit opportunity. And with that value, we will be able to ensure that every time we are meeting control loop requirements when having other nodes in the network. I will let Mete finish this presentation with the conclusions. So thanks for your attention.
Thanks, Eduardo. So just some concluding remarks, really. So the architecture is there to deliver customer features, but the ever-demanding requirements of features is increasing the complexity of domain-based architecture. And we think that complexity can be eased by transitioning to a software-defined vehicle. And when we make that new architecture, the main focus should be to make it easy to deliver customer features. So JLR and ADI, we have together demonstrated as a starting point how a challenging low latency application such as suspension can be implementing using 10^T1s and E2B's remote control capability. So you will see the requirements that we used. Again, like I said, these are the requirements coming from the capabilities of today's domain-based architecture, and in the future we would surely want to make that even better so we can enhance or advance our algorithms and capabilities. So that's all from our side. Thank you very much for listening.
Okay, thank you. We'll open it up to questions for Attila and Eduardo. Max, I think you're first.
Thanks for the presentation. I'm going to ask a somewhat unfair question, at least to half of the presenters. But coming from an OEM in the past myself, do we need to find an excuse to get faster networks to our systems in order to avoid this latency that you described with PLCA 10 megabit? Do we just need an excuse to actually put a gigabit link there or a 5 gigabit link and then at least reduce the problem a little bit?
So I guess it's an easy way out to just introduce those multi-gigabit networks as your Ethernet backbone and just rely on the fact that your data will be transmitted and out of the egress port quickly so that you don't really need to worry about managing traffic. But I think it's not the efficient approach. So I think we need to be more diligent in how we engineer and manage the traffic in our networks and make it much more optimized, much more efficient, and not just straight jump onto opting for the high bandwidth option. That's my personal view.
I agree with you. We need a better excuse to do that. Yeah. Thanks.
Any other questions? Yes.
Hopefully hear me. You were able to prove this kind of in a domain way. You had one application running on a central. But I think your conclusion at the end was that when you add additional functionality to the central compute, you're going to have much more complexity behind it. And maybe just to sort of back of Max's question, is that the time when you may need to make sure that how is your latency going to impact on the overall delivery of your final output? Will that not have an impact at the end?
If I understood the question, Harry, so having multiple domains in the compute,
Yes.
operating all on the same hardware.
At the moment you've got one application running, but you'll have multiple applications running.
Yes.
So how are you going to make sure that you can actually deliver and meet those target times?
Yeah, okay. I think one of the key things that makes SDV possible going forward is the availability of these really high performance SoCs and compute modules. If you think of today's domain ECUs, they run at single or multi-core microcontrollers running at clock frequencies of 100 megahertz, 200 megahertz. So when we make that transition to putting the logic into a compute, we are hoping that we'll be able to use the compute's capability of running at gigahertz speeds and having access to many cores and the safety islands, etc. So I think that will be a key enabler for making sure that the latency requirements are met going forward.
Okay, so are you planning to make that step into putting more application to test your theory in so that we can have other applications running at the same time?
As a next step,
Yeah.
yes, we definitely do, yes.
Okay, thank you.
Thank you.
Question over here? I think so.
For your micro, were you using a bare metal implementation or were you using
it
a
was bare
RTOS? So bare metal?
Bare metal, yeah.
Did you try to experiment like running with an AutoSAR?
Yeah, I think
stack?
that's next steps on the demo. Yeah.
Okay. And the 2 millisecond requirement, that was just at the current suspension module?
Yes,
that you have?
exactly. So, like I mentioned, so we wanted to make the requirements what today's domain architecture can achieve as a bare minimum, so that 2 millisecond end-to-end latency is today's iteration and how that system works with its limited microcontroller and the AutoSAR stack.
Okay.
Yeah.
In your testing, did you see how much space, like headroom that you had between your worst case and the 2 millisecond requirement?
So how much time we have spare between?
Yeah.
Yeah, it was 680 microseconds for
Okay.
a bar.
Yeah, and we believe if today's microcontrollers can do it, we believe the SoC will be able to do it.
Okay.
So.
Lastly, how did you implement GPTP on half duplex T1S?
Sorry?
How did you implement GPTP on T1S? Given that my current understanding is that.
So our device can support GPTP Grandmaster to be GPTP Grandmaster in there. That's the MAC5 device. So then we synchronize all the rest of the nodes on that GPT timestamp from the central MAC5 device.
Okay, so this is part of ADI's implementation. Okay, thank you.
Thank you. Thank you.
Okay, time for one more question if anyone has one. Nope. If not, thank you very much for the presentation.